Myself, Kara, as well as Arian, Thomas, and Zachary are on a team of junior engineers working for a consulting firm. The consulting firm, known as Alpha Corp Industries, specializes in designing and commissioning separation technologies. Upon receiving a request from Alpha Corp, we as a team have a successful proposal to separate hydrogen gas, resulting in over 98% recovery. Our solution involves metallic membranes made from palladium-based alloys, which will ensure a proper separation of hydrogen gas. We are thrilled to discuss our results and propose our solution to you today.
In the current global energy market, the demand for hydrogen gas is growing due to the drawbacks and limitations of fossil fuel usage and the growing concerns of global warming. The current market for hydrogen is approximately $130 billion US and is expected to reach upwards of $200 billion by 2025. Hydrogen gas serves as a clean and renewable energy source that can replace current methods, as its production's only additional major byproduct is water vapor, which is more sustainable than the unwanted emissions of current fossil fuels. It has potential applications in a variety of different processes and can be produced through a variety of methods such as conversion of natural gas or from renewable sources such as solar, wind, and nuclear power. It has usage in the production of fertilizers, metal, glass, electronics, and can be used as an alternative fuel source for vehicles, among many other examples. In the case of fertilizer production, hydrogen gas is used as feedstock in the Haber-Bosch process by petrochemical companies and ammonia producers. Therefore, the potential gain to be made by Alpha Corp by fulfilling this growing demand for hydrogen gas through the conversion of inexpensive natural gas is significant. We have been provided the task of evaluating the current initial design and simulation for this conversion process and providing a separation process that will assist in enriching the hydrogen gas production purity within the given restrictions provided.
To begin, Alpha Corp Industries is a company that focuses mainly on extracting value from natural resources such as minerals and petroleum. The company is currently in its preliminary stages of designing a new $2 billion chemical plant in Texas. As displayed in the flow sheet is their design, with an overall goal of optimizing on the growing market for hydrogen gas. It can be seen that there are currently two outlet streams within the process. One is at the bottom of the flash drum, containing 99% water being sent to wastewater treatment plants. Within the red dotted box in the upper product of the heat exchanger, it can be seen that the company has currently reached an output of 59% hydrogen gas. However, Alpha Corp Industries has little experience in further designing a separation process to enrich the hydrogen gas to a minimum of 98% recovery. This is where our team of junior engineers comes in handy. As a team, we have a valid separation solution that will be proposed to you today in detail, which will enrich this hydrogen gas. Furthermore, we have a solution that will ensure that the hydrogen gas gets pressurized so it can efficiently be transported via pipeline to nearby clients. In general, our solution includes the addition of metallic membranes made from palladium-based alloys, and we are excited to present this to you today.
Palladium is classified as a dense metallic membrane. Now, gas transport through the membrane occurs through solution diffusion mechanism, where hydrogen dissociatively adsorbs and diffuses through the metal rather than moving through pores. Other than palladium, most metals require an energy input in order to overcome an activation barrier to adsorb hydrogen. This leads to higher pressures and temperatures being a necessity in the process. On palladium surfaces, the dissociative adsorption of hydrogen molecules occur with little or no energy due to how naturally selective palladium is to hydrogen. This selectiveness also makes the separation of hydrogen much easier in the process. Metals such as vanadium, niobium, and tantalum offer higher permeability when compared to palladium. However, when exposed to hydrogen at operating temperatures and pressures, these metals undergo a process known as hydrogen embrittlement, where they lose flexibility and become mechanically unstable. Additionally, these metals are prone to the creation of surface oxide layers, which lead to a decrease in hydrogen transport. The figure compares permeability of various metals to a wide range of temperatures. It can be seen that while palladium offers lower permeability compared to the other metals, it can operate within a wide range of temperatures, making it much better suited for industrial application. Now, palladium is commonly alloyed with other materials for various benefits. Common materials used for alloying are silver, copper, and gold. Alloying with these metals result in increased permeability when compared to pure palladium, better resistance to poisoning by different constituents in syngas like carbon monoxide and carbon dioxide, increased thermal stability at higher temperatures, and reduced cost of production, especially when using copper since it is a cheap metal. As seen in the figure, the weight percentage used for alloying results in varying hydrogen permeability. To maximize permeance in palladium membranes, silver alloy weight percentage should be in the range of 10 to 30%, copper alloy weight percentage around 40, and gold alloy weight percentage in the range of 5 to 20%. Now, silver is one of the most commonly highly studied and utilized metal for alloying with palladium and can be found in existing commercial applications. Looking at the figure, we can see the improvements in hydrogen permeability and flux with the addition of silver to the membrane. The addition of silver also increases the hardness, mechanical stability, and chemical inertness. The figure on the left shows the hydrogen permeation for pure palladium and palladium-silver alloy membranes at temperatures of 300 to 550 degrees Celsius and with a pressure difference of 400 kilopascals. Overall, the hydrogen permeation increased as the testing temperature increased, and the hydrogen permeability was significantly enhanced by alloying with silver. The figure on the right shows hydrogen flux versus the pressure difference for palladium and palladium-silver alloy membranes at 550 degrees Celsius. It can be noted once again that the addition of silver to the membrane significantly enhanced the flux, which is seen increasing linearly with the square root of pressure. Now, the presence of additional gases in the feedstock can affect the membrane performance and lifespan. These adverse gases poison palladium membranes, resulting in decreased flux and irreversible changes in some cases. Usually, these gas molecules are adsorbed onto the surface and hinder the dissociation of hydrogen onto palladium, resulting in reduced mobility of hydrogen atoms located on the palladium surface. Sulfur, carbon monoxide, and water vapor are common gases that are known to poison palladium membranes. Sulfur is more problematic as it leads to irreversible changes and eventual destruction of the membrane over time. In the case of Alpha Corp's feedstock, sulfur is not present and does not need to be accounted for, making the use of palladium membranes even more attractive. Carbon monoxide and water vapor cause reversible changes on palladium, which lead to a decrease in permeability and flux. The product stream in Alpha Corp contains 16% carbon monoxide, which is a cause for concern. However, alloying changes surface reactivity and electronic structure of palladium and help negate the poisoning effect of carbon monoxide. Additionally, operating at high temperature reduces it as well. Therefore, by alloying it with silver and operating the process at around 550 degrees Celsius will mitigate the effects of carbon monoxide on the membrane. Finally, water vapor only accounts for 1% of the product stream, which can be neglected once again due to alloying and operating temperatures of our process.
It is without a doubt that palladium is the most widely used membrane material for hydrogen permeation and is infinitely selective to hydrogen while demonstrating a high recovery. For example, when compared with their counterparts such as polymer membranes, palladium-based membranes have the distinct ability to achieve hydrogen purities as high as 99% or higher. This outcome, however, is only valid as long as process requirements and pre-treatment methods are handled appropriately. To reiterate, our goal as junior engineers is to achieve a minimum of 98% hydrogen from an initial composition of 59%. It is evident that this can be achieved in a single step with a palladium membrane, and the process must be carried out at relatively high temperatures. It is crucial to note that palladium membranes are often damaged by hydrogen embrittlement, which could occur below the critical temperature of 293 degrees Celsius and a pressure of 20 bar. It's also important that we don't exceed temperatures around 650 degrees Celsius, as palladium may be subject to deactivation upon these extremely high temperature conditions. With that being said, for our process, we'll be making improvements to the membrane inlet conditions to ensure that the palladium membrane can result in an ultra-high recovered hydrogen stream. We will now be looking at our improvements being made to the design more in depth. As a team, we have made additional improvements to Alpha Corp's initial design. To begin, as stated earlier, we know that in order to achieve a high recovery, the membrane inlet temperature must be high, somewhere between the range of approximately 300 and 650 degrees Celsius. We will be achieving this temperature by adding a series of heaters to the system prior to the membrane entrance. These heaters will be placed after the heat exchanger in the process once water has been removed. We will also be adding a compressor to further increase the pressure of the mixture right before the membrane entrance. With valid high temperatures and pressures, our mixture is ready to enter the membrane. Once we achieve a permeate stream of hydrogen, we need to further compress the gas to achieve a pressure of 200 bar, allowing for the gas to be stored in pipelines. As well, the resulting hydrogen gas will also be cooled and will be stored at approximately room temperature conditions, being about 22 degrees Celsius. And there we have it. Our plan to improve the design will result in recovered hydrogen readily available for use. However, we need to keep in mind that the membrane will also produce a stream of waste, which will be dealt with accordingly. The waste analysis will be discussed further on in our solution, but for now, let's visually take a look at our design improvements displayed in a piping and instrumentation diagram. As displayed here, our generic PNID shows all improvements made to the system, from inlet gases to pipeline storage and waste disposal. Within our process, you can see that we've made improvements to the upper outlet stream of the heat exchanger labeled HX4. From here, we have added our series of heaters with a 2-bar pressure drop in both, followed by a compressor labeled Comp1. These improvements to the design allow for the desired inlet temperatures and pressures being around 550 degrees Celsius and 20 bar respectively. The mixture of gases will now be able to enter the palladium membrane as the inlet conditions are valid. The outlets of the membrane consist of a waste stream and a hydrogen stream. For the hydrogen stream, we'll be cooling the gas, again with a 2-bar pressure drop, then sending it through a series of compressors. The 2 compressors in series ensure that the 1:5 pressure ratio is not exceeded. A final cooler is added after the series of compressors to store the recovered hydrogen at 22 degrees Celsius. With this proposed PNID, we'll be able to simulate our design in Aspen Plus. We began the process from the heat exchanger outlet while disregarding the flash drum in the original design, as the water has already been purely separated and will be sent to the wastewater treatment plant. The inlet conditions are displayed at 11.5 bar and 50 degrees Celsius with a molar flow rate of 9,262 kmol per hour. The inlet includes 59% hydrogen, 21% carbon dioxide, 16% carbon monoxide, and negligible amounts of nitrogen and water. Prior to entering the membrane, we heated the streams with a series of heaters to 350 degrees Celsius while obeying the 2-bar pressure drop through each individual heater. From here, we compressed the gases to increase the pressure to 20 bar. The compressor also increased the temperature of the gases to around 566 degrees Celsius, which is optimal for our membrane. Our compressors are assumed to be isentropic, working with 80% efficiency. From here, our conditions were valid and the components were able to enter the PD membrane, or in Aspen terms, the SEP block. The SEP block was used to eliminate all components that simply could not pass through the palladium membrane. Once pure hydrogen was obtained, we cooled the gas with the cooler and increased the pressure with a series of compressors. A final cooler was needed to result in stored hydrogen at room temperature, and the condensers increased the temperature drastically. This resulted in nearly 100% hydrogen recovery, which is stored at room temperature being 22 degrees Celsius and the appropriate pressure of 200 bar. The hydrogen is now ready to be stored in pipelines. All other waste exiting the membrane has conditions of 566 degrees Celsius and 20 bar. Now let's take a closer look at the outlet results achieved from our simulation. The following displays the results achieved from the Aspen Plus simulation with the SEP block being used as the PD membrane. There are 2 streams obtained from the PD membrane. From here, we can visualize the molar fractions as well as the mass and molar flow rates. First of all, from the stream labeled pure H2, it can be concluded that hydrogen gas is being achieved and is ready to be stored at the desired pressure of 200 bar. From the stream labeled other, the components are displayed as they are released from the membrane. These components include carbon dioxide at 54 molar percent, carbon monoxide at 41%, and water and nitrogen gas both at 2.5%. These components were simply unable to pass through the palladium membrane and act as waste components. A waste analysis will be computed to determine the best possible solution for dealing with the waste stream.
There is a number of waste generated from this process, and a number of options are available for dealing with the waste generated. The retentate stream is mostly comprised of carbon dioxide and carbon monoxide. This gas mixture should not be recycled back into the system, as there is not a considerable amount of hydrogen present in the stream. The carbon stream can be sequestered via carbon capture and storage, CCS for short. There is a cost associated with this, but it is something to consider as carbon taxes are set to be 170 Canadian dollars per ton of CO2 generated by the year 2030. The gas mixture could be flared also, or just vented into the atmosphere. This would result in emissions. The palladium alloy membrane itself can be recycled. The palladium later separated from the support can then be treated to solubilize the palladium and, where appropriate, the alloy metals to obtain salts that can be reused, for instance in the preparation of new palladium membranes. The recovered supports can also be reused and repurposed. The capital cost breakdown results in a capital cost range of $105 million to $169 million. The capital costs of the heat exchangers and compressors were accounted for since the streams need to be compressed and heated prior to membrane separation and then cooled significantly after membrane use. Heat exchanger capital costs were computed using the area generated from Aspen, and then the Woods cost estimation for process industries. These costs have an uncertainty of plus or minus 20%. The compressor capital costs were also appropriated using Woods and have a cost uncertainty of plus or minus 40%. The cost of the membrane was found by utilizing the available flux for a palladium-silver alloy membrane, finding the area of the membrane using the flow, and then computing the cost on a square meter basis. There was no uncertainty available for this computed value, so it is assumed that the costs are accurate within plus or minus 50%. The capital cost is presented as a range, since there are different costs associated with the retentate options. Carbon capture and storage would result in an additional $64 million in capital investment. Gas flaring would require a furnace, which would cost an additional $500,000 in capital, and venting would result in no capital investment. Both these costs have been assumed with an uncertainty of plus or minus 50%. Operating costs were computed by assuming that the process operates 8,000 hours a year. The operating costs include utilities required for heating and cooling. These utility costs were approximated using Aspen, as well as the utility costs for each type of heating and cooling. Membrane costs were obtained by literature, and considering the lifespan of the membrane is around 5 years to get the operating costs. The cost of operating CCS was found utilizing literature as well. Using these values, the operating cost ranges from $31.38 to $35.98 million per year, depending on what the retentate option is. The cost per ton of hydrogen then is approximately $532 to $708 per ton of hydrogen produced. Now, it's crucial to consider that the cost of palladium is rising. As you can see on the graph, the price does fluctuate. However, there's a general positive correlation occurring between the cost of palladium per ounce and the year for the last 40 years. Prices are expected to continue to rise as the supply is below the demand of the material. This has been the case for the last 8 years now. This is why alloying the membrane is considered, as it is cheaper, more attainable, and actually aids in increasing the flux of the membrane. Recycling of these membranes also makes the membrane more affordable. Currently, efforts are being made to make sure that they last longer, are more cost-effective, and more attainable. Now that we've gone over some general aspects of palladium membranes and hydrogen purification, the pros and cons of the technology and a comparison will be done. To summarize, some overall advantages of using palladium, specifically palladium alloy membranes, for Alpha Corp scenario include these membranes are distinguished in terms of hydrogen separation and purification due to their high permeability and selectivity for hydrogen, as they can attain high hydrogen gas recovery and purity up to 99% given the inlet conditions. This can be achieved using a single pass membrane in order to attain this requirement. The overall process is rather simple, given the minimal maintenance and pretreatment needed. In addition, this membrane separation technique has relatively low energy usage, resulting in it to be environmentally friendly and cost-effective during operations, especially when compared to other hydrogen separation techniques, which will be discussed further on. Lastly, these membranes can be recycled and reused or repurposed for new membranes or other materials, contributing to the environmental aspects of the process.
Palladium-based membranes have some deficiencies as well. Firstly, when used for the application of hydrogen separation specifically, the membrane's exposure to carbon monoxide causes the permeation of hydrogen to decrease with continued use. This problem can be resolved, but only by increasing the overall operating temperature of the system. The minimum recommended temperature for the separation of hydrogen is around 300 degrees Celsius. And as can be seen from the PNID, we implemented an operating temperature of around 550 degrees Celsius. This increased temperature is used to combat another main deficiency, which is to avoid embrittlement and cracking. When used in this application, having the membrane operate at a temperature below 300 degrees Celsius will increase this risk and will result in the lifespan of the membrane, which can normally last for a period of 5 years or more, to be reduced. The increase in temperature to alleviate these potential shortcomings does, however, come at a cost. With the operating temperature increased to around 550 degrees Celsius in our system, the increased cost of utilities to maintain this increased temperature will increase as well. Due to the previously stated issue of permeation when used in this application, palladium membranes require a relatively large surface area and must be ultra thin, approximately 1 to 10 micrometers, to be effective and maximize the overall flux. In addition, the minimum operating pressure recommended for the separation of hydrogen is around 2 megapascals. This level of pressure is also required to maintain the necessary flow and flux through the membrane. Due to palladium being a metallic membrane, the amount of pressure required to increase the flux is more than would be required of a microporous membrane, as the relation of pressure to flux, when compared, is not 1-to-1. This increased pressure will come at an increased cost to the utilities. In terms of overall cost, when compared to the two alternative presented methods of pressure swing absorption and cryogenic distillation, although palladium-based membranes provides a more economical solution, the market price of palladium is high and has been continuously increasing. Looking at the current trend and its likeliness to continue, the long-term effects of increased palladium prices should be considered as a potential deficiency moving forward. These advantages and deficiencies of palladium membranes were considered when looking at the process requirements.
Here, we are comparing the palladium-based membrane to other models, including pressure swing absorption, or PSA, and cryogenic distillation. In comparison to the palladium membrane, PSAs are capable of producing ultra-high purity hydrogen up to 99% while operating at high or low pressures. With that being said, however, they require complex control schemes and have a much higher operational and capital cost. PSA control involves precise depressurization and repressurization steps between beds and bed cycle time and must be closely controlled to prevent oversaturation of the bed, which can result in offset hydrogen. As well, temperature is a critical factor as high temperatures reduce the absorption capacity and increases the capital cost, so temperature must be closely maintained. PSAs tend to have a lower turndown capability than membrane units. Next, cryogenic distillation is much more capital and energy intensive than membrane separation in PSA, as well as operationally challenging. For these reasons, cryogenic distillation used for hydrogen purity is far less common. However, it is highly effective for streams that contain methane. To conclude the comparison, it is evident that palladium membranes are most feasible when it comes to capital costs, as well as maintenance and pre-treatment methods. When comparing startup times, palladium membranes typically have the shortest time, and they ensure a high hydrogen recovery as long as inlet conditions are met. Overall, there is a high comparison between all three technologies, and they all have proven to be successful with separation processes. But what does the future in regard to research look like for these membranes?
Up to date, palladium is the most studied metal for preparing hydrogen-selective membranes. Over the years, palladium membranes have been investigated in numerous applications where hydrogen gas is involved and has been an extremely popular method of separation. In addition, these membranes have been gaining increasing interest throughout the years with an increase of research publications. This trend can be observed in the figure that shows the number of scientific documents published by year and region considering hydrogen, palladium, and membranes. The increase of related publications during the most recent years is due to a greater awareness on environmental protection and renewable energies development, where hydrogen emerges as a very promising clean energy vector that requires purification. As we have previously reviewed the deficiencies, such as embrittlement and cracking, it is also important to note that various researchers in the field are tackling these problems. Main efforts are focused to reduce the cost of these membranes and to increase its membrane resistance and lifespan. Palladium is expensive and has a growing demand, and its price is expected to keep driving up. In the future, strategies will continue to be studied to reduce the cost of the membrane by minimizing the amount of palladium required and increasing the lifespan of the membranes. As research for improvement continues, hydrogen is prospected as a sustainable energy carrier for the future of various applications, and is without a doubt a growing industry as palladium membranes are being actively used and researched globally. The separation of high purity hydrogen from the hydrogen-containing gas mixture using palladium-based alloy membranes is an effective process for the commercial production of high purity hydrogen. Our proposed solution using palladium-based membranes provides Alpha Corp with a method that yields high product recovery in a way that will be cost-effective and environmentally sustainable going forward.
That'll be it for today. Thank you for your time.